Welcome back to Cloud Computing and Big Data, our lecture 12 today on Docker and container management. In the first part of the lecture, we learned a little bit what's the difference really between so-called Docker images and virtualized images or VM images. And we learned essentially that Docker has a key benefit of not carrying around this operating system in these VM images. And of course, there are lots of different advantages that go with that they have an easier portability, you have less sizes of these images. And the interesting fact is that today you will find almost all clouds really enabling to basically make use of Docker images. And I have to say, even academic high-performance computing centers, even academic environments actually supporting Docker or at least Singularity today, which is a very similar concept, and I will go back to that in the end of the lecture. There's some certain interoperability to this, but it has really made an impact in the community, especially for data sciences. That means when you think about parallel and scalable machine learning and deep learning, to have all the right packages, to have perhaps even specific data sets already readily available. And this is a notion of Docker and Docker images with basically building a container environment which is working on its own. So it's the containerized applications, containerized software really means that it has all its dependencies solved, right? So it's on its own existing, it's on its own working, and with this you can shift it around, you can pull it around. We have seen the analogy in the first part of the lecture, which was really about, putting containers that we already know from our daily life, from SumSkip, from IMSkip, from Smyrline, on a ship, on a boat, but maybe also on a railway or basically on a truck driving through Iceland. And all of that is possible because it's a kind of certain de facto standard in the community. Nobody really says you have to use Docker, right? Of course, but if you use Docker, you have a massive flexibility. And this is something which is, I think, well understood if you look into the AWS service portfolio around it. And the way how you have to see how it reflects also to this microservices notion that we have seen. Of course, again, it would be bad to do a big, bold Docker images, one image, which can do everything, right? You would again think about, shouldn't we do this individually on certain components, which some of the applications actually has already alluded to, and also the video. So essentially, we're talking about different Docker containers have to work together in order to make something happening. And with this, you're very easy into a certain, server and lifetime management of all these Docker instances, right? A Docker image is not alive. Once you take the Docker image, you deploy it on a certain server, it becomes a Docker instance, almost like the VM instance we discussed in lecture 4 already. But the Docker instance, of course, is very similar, but also may also work together with other Docker images and instances at that point in time in the life cycle. And in order to manage this all and to enable this microservices that we have seen in the video, but also this individualization and flexibility, you need certain software tools that actually help you with building this. And the Kubernetes was one example of it that we have seen, which is also open source, which is complementary. It has nothing to do with containerization as such. It is actually thinking much more about worker nodes again and master the paradigm you already know a little bit from MapReduce, thinking about how I can manage all of these containers, which is really the role then of Kubernetes. So that summarizes a bit what we did in lecture 1, part 1, lecture 12, part 1. But what we want to do in the second part now of the lecture 12 is really thinking about a little bit more what could be unique aspects. So I said earlier also that we can have 5 to 6 lectures on this, at least, if not more. And of course, it's a very big topics. And I think in future university schedules in software engineering and engineering, there's probably a whole course just on containers. And in order to reflect that a bit, I would like to pick here in the second part some advanced computing concepts with respect to containers and exactly put some light on some examples which are relevant. Of course, I picked the parallel scalable machine learning elements here and there, but also thinking about more engineering use cases, really, when you think about our faculty. So what could be interesting approaches to this and how cloud computing can really support this. So we look at some solutions, really. And here it's again an idea of how you combine now all these different pieces we learned in the course when you think about microservices. Now, I want to realize an app for IKEA, for instance, that does an image analysis and really knows directly which product I'm talking to. Here I have this nice artificial flowers that you see everywhere. And I will actually make a photo in some store and want to see what options does IKEA have in this. So I have an image analysis basically component, which requires maybe deep learning, but then I need also databases and some modeling for the deep learning. So I combine here different aspects of services, which you actually can use in the Google Cloud, just to show you also, again, the different clouds, right? So we have been in Google Cloud before for different platform as a service operations. And here for industry solutions, you have really a wide portfolio of platform elements you can choose from. And of course, one is a Kubernetes engine that you know, which of course supports then also containerized applications with Docker. But in order to do so, you basically combine now the world of Jupyter for modeling this, to have a deep learning engine, and then Kubernetes to put it in the Google Cloud, and you have something very similar, basically, as you have seen in the AWS cloud, which is possible. Of course, here we are more on the developer side. If you remember, the platform as a service, Google Cloud, and so on is much more of thinking now how we can actually create a product out of this. So how we can do an app like this that you see right now here on the screen. And of course, this goes for lots of different people in different stores. You see the kind of users of these systems are very broad. And if you look into the industry solutions of Google Cloud, you will find many of these examples, and almost all actually have this notion of containers, right? So basically they're often underpinned, as I would say, by these containerized applications to scale up. We learned about horizontal scaling, and then here and there it's also about portability. So these vendors don't want to be, let's say, completely dependent on one of those cloud providers. So by sticking to Docker containers, you have also a good chance when you do it, perhaps also in a Google, in a Kubernetes context, to really, be portable between different cloud vendors. And that's what you see here when you do a Kubernetes hybrid cloud approach. You would have your app and Kubernetes supported. The chances are that you basically go to the Google Cloud platform here, but basically can deploy it even on your own data center or other clouds, as we learned from AWS, and also MS Azure, of course, that is supporting Docker and Kubernetes applications. Of course, this means you have to do it in a specific way. You have certain deep learning containers, which maybe have all the data science frameworks, so TensorFlow, Keras, but also maybe PyTorch. MXNet, we have seen in one example also, there are different ones. You have a certain container registry where you upload all these different ones. We have seen this is existing in AWS. It's in Docker Hub, in open source version. And of course, the Google Cloud also has a container registry, right? And that's again the same idea, storing, managing these Docker images that you then basically download or pull, as we would say, to some of the computing entities in order to make an instance, right? So essentially saying a Docker image is dead, right? It's just a recipe, as we call it. It's just something which instructs something how a container could look like. The real container in its real working solutions would be a Docker instance, which means it is combined with some form of computing, with some form of infrastructure, of course, in order to get it run. And in order to scale, we have seen different approaches there to do this. And one of them was the AWS cloud, with this different services. But essentially, we'll see that everywhere in all these different clouds, from MS Azure, AWS, and Google Cloud, they have one way of running it in a different way and different fashion. Of course, the Google Cloud is a little bit looking more on thinking about the different, let's say, integrated development environment, again, a bit more looking a bit on, cloud developers, then perhaps AWS combining different pieces more on a software as a service level. But in a way, the differences, as I said earlier, between infrastructure as a service, platform as a service, and software as a service are more and more, let's say, vanishing. So you find really an integrated set of services. We will also see, when it comes to your own data center and your own cloud, we will look in the OpenStack cloud operating system. So how you can also there see in OpenStack how Kubernetes is nicely supported, how the idea of containers is nicely supported. And you have open source components that easily manage this. So to be basically in a hybrid cloud, hybrid in the sense that you combine your private data center cloud. So private cloud is something you learned earlier in one of my lectures. Combined it actually nicely with public clouds like Google or other clouds like AWS and so forth. That's why we call it here a hybrid cloud. But the point is, you do your application still in your Kubernetes environment or based on the so-called Kubernetes cluster setup. And then you're basically very free to deploy it on this hybrid setup, which is, of course, a key benefit. And some of these components we will learn also lecture 13 about it. Now, when we have another example, we know from previous lectures, it's really hard to deploy a certain deep learning setup, right? It sounds so easy, just downloading TensorFlow. But if you want to have it scalable, you need it with the right, let's say, lower level GPU libraries like Nickel, for instance, for, let's say, NVIDIA. But also we see very soon much more heterogeneity of accelerators coming along, right? You have Radeon, you have basically different vendors providing accelerators. With this, we have also different types of underlying libraries. And then you don't stop with TensorFlow. My students, my PhD students, you have seen Rocco, Shadi, they use PyTorch, they use TensorFlow, they use Keras on some certain occasions, and combine that even with libraries like scikit-learn, which are very powerful still, although it's more, let's say, a serial setup, what you do with scikit-learn. It has lots of statistical elements that you still need. And by all packaging this is, of course, a real challenge. And if you get this, let's say, in one of the Docker images already ready, this is, of course, very, very helpful for developers of AI, for developers of machine learning, to not cope too much with the IT. And these are things you know already. I actually had done this in my lecture already earlier. It should sound now very much familiar with the idea of the AWS AMI images, right? If you think about what they did in this VM images, was exactly the same idea. When we used this, I demonstrated in practice. When you go to this and you see all the different packages installed already in an AMI, let's say Amazon package there, Amazon VM image, so that you essentially have all the packages already there. So the difference here is when we talk about containers, of course, that here would have a very similar consistent deployment of all these packages, but we don't have, let's say, the Amazon operating system or Linux or whatever, or basically any operating system there. So we're talking about essentially a container. And this is one of the benefits. And when you basically use that in different clouds, and here's again one example now in the Google Cloud, if you have this deep learning containers, which are really then this Docker-based images that you can just use with all the popular frameworks, and it's already with underlined libraries, as I said, Nickel for NVIDIA, performance optimized. It works with those GPUs and it's just ready to deploy. Don't underestimate this. If you go to the field, you buy your own GPUs in the future, and your boss says, just deploy me a TensorFlow, PyTorch, and MXNet and try what is the best performance with all of the three. And actually now we have this on scale, combine it with Horowat, combine it with DeepSpeed, which is a new framework. You will basically sweat a lot, because having all of that installed, having all of that configured could mean hell a lot of time. And my PhD students here and there can actually give you some examples of those being through this. So in this private clouds and in this idea also combining them with public clouds, there's lots of tension of different versions. You have to, let's say, port your applications maybe from your own local Jupyter notebook suddenly to a public cloud provider, and really nothing works directly because all of them have different versions of some certain kinds of Python APIs. So it's actually not so trivial. When you combine this now easier in these Docker images, in the containerized worlds, you agree on a certain set of versions. It's much more, let's say, compatibility and interoperability that you make happening with this. So thinking about then PyTorch, interestingly enough, I found also a cool example here of Alibaba, not because it's now important to know all the details of Alibaba Cloud and so on. Here, I would also be a bit careful in the lecture. We learned already in one of our data protection elements that, outside EU, you'll be on your own, right? So whatever happens in Alibaba is something which is not so easily understood in legal frameworks. Unfortunately, today we had this GDPR, as you remember, but this is a very European framework, which is very good and brings Europe, I think, very, very far in front. Still, it has its problems, of course, but still, if you now go to the international setup, many things are not really understood. So what happens, if someone like Alibaba would go bankrupt? Who owns the data? Who has the right to maybe work with the public data that you put in there? So all of these things, you have to be a bit careful on this. However, of course, if you look on this Alibaba Cloud, there's no doubt that they have a very strong service portfolio as well, right? So strictly speaking, as a neutral university professor, you would say you will find very much advanced services there as well. So there's absolutely no problem with that. It's just more, I don't like to use it very much because usually we having this legal aspects, of course, which is perhaps a bit better understood with, US hyperscalers. But I don't want to be biased here, so I give you a neutral view that, of course, also Alibaba Cloud offers a lot of comprehensive services. And the point being is here is it has not only this deep learning powerful frameworks hosted. You see here a little bit, when you look into the Alibaba Cloud, it has, of course, lots of services for image recognition, image search. We have learned already in one of the lectures, a natural language processing, intelligent speech interaction as services for this, translation and so forth. So definitively lots of it is happening. But if you look into the inside elements, you still find lots of containers. You will find different images. You find the power of virtualization. And the beauty is, again, that, of course, some of those are really comparable to those we have already tackled before. As I said earlier, it's really a highly likelihood if you stick to this certain, let's say, deep learning packages, but then also use the power of containerization, that you can easily move your application, let's say, from Amazon, Google, Microsoft to the Alibaba Cloud or vice versa. And this is, of course, a very helpful element, again, showing you perhaps one very unique element now, because basically we had never the Alibaba Cloud before. And of course, I encourage you to have a look at the references, to look and check out what actually Alibaba is doing. It's not only doing PyTorch, of course, it has many different services and is a very strong cloud service provider, of course. You see also they team up with the right, let's say, set of vendors for cutting edge technologies like NVIDIA. No, question about this. They have cutting edge technology under the hood. So with this, I want to shift a little bit to another player that is usually very common in this field. You would say, when we learned about Amazon, Microsoft, and Google, what's in with, IBM? And IBM is usually a very strong element or candidate of a cooperation partner in terms of parallel computing. In the past as well, they had the Blue Gene series for data centers. They have, let's say, a very huge diversity of machine learning tools, which is often used. For instance, I had very much projects with SPSS modelers in the past, where at times it was not really a cloud tool. In previous years, it was more a license tool you install, really. But of course, everybody was going more and more to this cloud setup of having, let's say, the software as a service model, when you remember, I talked a little bit about AWS SageMaker and one of the ideas of having a complete, let's say, machine learning, data mining setup within the software as a service offering from AWS, which is a SageMaker. Think about that IBM can do very similar things with the so-called Cloud-Pak for data. It's basically a Red Hat OpenShift platform, which internally, again, works on Kubernetes, which internally takes already, basically benefits from the containerization approach. And you have different nodes, so you would actually program that more as a graph, but we know already that even TensorFlow is compiled into a graph. And you see here some examples when you look into what SPSS modelers offer, and you would have a graph setup of really combining those and then have many different data mining or machine learning models, the K nearest neighbor, neural nets. We have not really talked much about, let's say, support vector machines, but we know something about linear regression models and so on. There's a huge set of so-called decision trees and random forests we touch based on here and there. So these are all different nodes you would basically combine with several statistical nodes or ensemble methods. If you want, you have a random tree approach, random forest approach, which then maybe grows 1,000 decision trees, which is, let's say, much better with respect to overfitting when you think about single individual decision trees. So there's a huge flexibilities in these tools. And there's, let's say, this Cloud-Pak really as a more or less software as a service offer, which you can use and really for data mining, for machine learning directly. And as examples, I gave you here the a priori, because you know it from one of the previous lectures. In lecture 11 and 11.1, we had this association rule mining, and this is also essentially supported. And then there are also more advanced algorithms supported, like Karma node or the association rule mode. I just provide this here as an example because you can allude to it, that like FP grows, like Karma, like Mafia, all they have different approaches to this problem and might be the better choice to do it. So the meaning of OpenShift and so on, we will discuss in let's say, subsequent lectures a little bit. It's more like how you organize all of that. But here you see another good example of, let's say, another cloud vendor that really goes into the right similar direction in what we have seen essentially with AWS SageMakers, or also this Google platform approach of providing very different platform as a service character systems like image recognition, like association rules, and so on. So a very powerful service, but of course also costly service. So SPSS is not completely for free. You have to subscribe to this model, as you know from earlier lectures, of course, where the return of investment is for IBM. Also saying that it doesn't stop with AWS, with MS Azure and Alibaba even. And here's a very good example I found, firstly, because it's related to Iceland, but secondly, also it shows you a very niche field, essentially, of how cloud computing now can be used. You see here the so-called UberCloud, which is very specifically more or less for engineers. So it's for people that deal with very complex, let's say, engineering problems. Although you see some medical application here, perhaps, which of course could be also seeing as one of the tough fields of engineering from some certain perspective of modeling and simulating. But essentially here I picked the example of this ANSYS, which is a very, let's say, popular package of, in engineering, like for instance, building airplanes, right? So this is a very strong package, and the UberCloud is particularly focused on those like COMSOL or OpenFOAM, where many CFD, computational fluid dynamics problems are solved with. So they provide very specific containerized, and that's the point here, containerized options for different cloud vendors. So the UberCloud in the end, we would consider a little bit as a meta cloud provider, because essentially they focus on the deployment on these containers in a very well set up way, so that it works with your simulation application like ANSYS, or maybe proprietary elements from Siemens, or even OpenFOAM, which is a CFD package that should work with this Kubernetes cluster setup in terms of managing and orchestrating really the Docker images you need to work on clouds. Now, which cloud you pick is essentially your choice. And that is, again, the beauty of the so-called de facto standard Docker and Kubernetes environments. So they are supported in all of those. And the new player, you see also HPE, which we should not forget because it's also still a strong player in the field. Also, when you think about Cray and high performance computing, but this is another story, maybe not here in the cloud computing course, but we will talk about this in the HPC course more. But in the end, you have this flexibility again as engineers to work really on these, let's say, UberCloud containers, which gives you lots of options then to deploy this. And Advania Data Centers also teams up with those and supporting these UberCloud containers. And this is, of course, something nicely now referring to Iceland. I have to also say, I'm not paid, of course, by UberCloud to mention this. I have to say, however, as a disclaimer here, that I know Wolfgang Gensch since a long time, maybe even more than 10 years. And basically, you know, we published together in 2011, but probably our connections go back to even more than this, where we created the first, let's say, supercomputing infrastructure in Europe called DESA, Distributed European Infrastructure for Supercomputing Applications. Today known more as PAAS, the evolution of this, the Partnership for Advanced Computing in Europe, and actually what is now in the transition period a little bit also with the Euro HPC joint undertaking. But these are all things we do more in the high performance computing course. But you see here a very good example how high performance computing shapes experts and also expert technologies really in the cloud computing world, which is very much overlapping. At that time, we called it more or less a grid infrastructure, grid computing, bringing components together, bringing different computing entities together to something which evolves now in 10 years to something called UberCloud. I just presented to you where Wolfgang is now the president of UberCloud, bringing the vision that we had 10 years ago to a much broader scale, to really industry. You have to see that 10 years ago, we did this mostly in academic scenarios. So there were still lots of servers down in the cellar in many companies, right? They would never have dreamed of cloud computing as it is today. And I think many of these concepts we do in science and engineering here, that you can see, for instance, here in one of the publications we had in DESA, is now realized, which are much more push towards industry by using containers, by using Kubernetes, but still many different concepts of applications we had already, let's say 10 years ago. But now you would say it's a bit on steroids. So UberCloud enables you, of course, a much more on-demand provisioning. You basically have a self-service platform. It is really secure. It has pre-packaged all the kind of, software packages you need, and is really, let's say, used today. And the slides I present here a little bit, let's say, given from, Wolfgang to me, because I think it's also good to have them from the right source. And it shows you a little bit an overview of where are the different applications in climate, in environment. It doesn't matter really. Drug design, very popular now with COVID-19 research in virology, drug design, and so on. But essentially, all of them have the problem of being very compute intensive in scenarios. And there, of course, the cloud computing is very important. Although you see here HPC user, you can see them also as cloud users interchangeably. You see aircraft design, which was perhaps ANSYS. But of course, here, being a cloud computing service, you have to focus on some market segments that give you really, let's say, revenues, right? So we see oil and gas, which is, of course, in the idea of green energy, maybe not so popular these days, but you can imagine that this market is very huge in terms of return of investment. So if you get the simulation right where you put oil and gas platforms, you're basically having a very good return of investment strategy. The same is true, of course, for all sorts of combustion, where we have research now with hydrogen combustion, which is not really understood very well, which is still a matter of research, thinking about, fossil fuel combustion we had before and things like that. Lots of these things are having, of course, also good return of investment and are really, let's say, used by industry. Also to show you the development of this, which is quite interesting in terms of cloud computing, and also now with this containers enables a complete, let's say, new branch niche, which would be previously maybe much more complex to deploy in industry scenarios, especially on this maturity. Basically, if you go back to 2011 or so, when we wrote the papers and so on, or when we thought about these things, at that point in time, we did it very academically, not really pipeline approaches, containerized approaches, which is now enough, enabling lots of stability, maturity in these components, but also then the portability across all these different commercial environments from Azure, AWS, HPE, and Google, and so forth. And you see that this is, of course, nothing which just directly comes, right? You start with some HPC container developments, and then you start with marketplace characters. And over years, you form something which is then really, really an interesting company, very, very specialized on one service offering, really, for engineers with all the right packages. Similarly, AI, right? We had before, it's another example. Here we have an example of being, very specialized for engineers that need certain packages like OpenFOAM or ANSYS, whatever it is you use for your different systems. But essentially being in a market niche, and this is all in a way really possible just because we have container technology. And that's why I provided in our lecture 12 today, just to realize another facet of this, that with containers, you have now a very standardized, or as I said, de facto standardized environment and infrastructure on a very high level. You have basically the operating system underneath. You have the infrastructure that scales underneath with, teaming up with all the cloud providers. So now you can really focus on your very specific, unique selling proposition in the application, which is for UberCloud here, of having prepackaged, let's say, images and for engineers ready to be used. And you see also it's incredibly used if you go to the website. And of course, here the idea is also to partner up with let's say, different software providers, because ANSYS is, of course, commercial software. So, but of course, on the other hand, commercial software providers like, all of these computer-aided engineering software providers, MATLAB is not for free. You have to pay for it. And many others, you can go on. OpenFOAM is maybe more a different example of being more open source, but many of those are maybe also commercial. But of course, they have also the self-interest of being better deployed, of being easier deployed by basically supporting and teaming up with the kind of these ready-made solutions. And I think this word ready-made really reflects it. Think about now engineers that want to design a new motor, like we see here as an example, or solve some other optimization problem, maybe a car crash in front of the wall and shear stress on materials. You can go on to the details, something what we much more do in the HPC course, which is complementary to this course. But you see that for an engineer to then spend all the time to setting up the IT infrastructure, to install all these different packages, to have the license agreements with, ANSYS, Abacus, with MATLAB, of how to use it in the containers or not, and how many users we can have. All of these setup is something where you maybe can use the UberCloud as a unique selling proposition and the niche market positioning really in between of those, and to make it much more easier for engineers to just have, this agreement. And the interesting thing, it's I think, ready to run. Just a short disclaimer here again, that I'm not really paid by UberCloud, right? I know Wolfgang, of course, since a long time, but that doesn't mean that, I put that here because I'm so convinced about this. I know many other in the cloud and HPC environment, but I think here you have a very unique example of showing you what it can bring, this container technology, and what can it bring to be very specific in a niche market. So whatever idea you have in some niche market, whatever it is, putting maybe, drones into the volcano now, since it's probably stopping, and, or having robots sent down there, to explore the the idea how actually all these caves have been built. Maybe it's a niche market, but potentially options for other products. Just saying this to give you also something for your world outside the academics. So if you have an interesting idea, chances are that within the infrastructures that are enabled by Docker containers, maybe also Singularity, you will find an environment which you can always choose very quickly. So if you're not satisfied with the AWS services anymore, you can switch to MS Azure, relatively simple, and you're not vendor locked. So you can basically use maybe a up-to-date service that suddenly appears in the Google Cloud just because it serves your business purpose better. So these are things which you have to think about when you think to the commercial environment. And we see also, while many students always asking me, so how that reflects Iceland, you see Advania, which is very prominent here in Iceland, or at North data centers. They also have certain components in this, which we look at, which HPC flow, for instance, which are also very close here in the course. So here goes the advertising for my course on high performance computing. So if you really want to know more how actually race cars are being built, how crash simulations work, you are in the field of computational fluid dynamics, which is essentially, of course, something for a HPC course. But today with UberCloud as an example, you will find this also in cloud computing very much, which then has many different approaches and basically different options to choose from here. The two basically main methods you have, what we also would actually tackle in the HPC course, which are more conventional CFD methods based on Navier-Stokes, but also Lattice-Boltzmann's approaches that we tackle in order to understand, for instance, waves, how they propagate through an ocean, and many different other fluid dynamics use cases. But this is more an advertisement just to give you also towards the end of this course, because we're approaching the end of the course now very quickly. We have done all the conceptual elements. We have, just a couple of links to further lectures left, which in my opinion should fill a whole university course. But we just have not university courses in that area right now, but probably in the future we'll have. And you see how that basically relates to engineering with finite elemente and so on. So smoke, how it propagates essentially through some space, or you see here the airflow around a car, which of course has to be optimized to be energy friendly, car crashes and so on. So all of this is relevant for engineers today, and they do lots of different tricks, and all of them have the side effect of being very computational demanding, hence the cloud, or essentially the high performance computing is required to solve those problems. Also here, very different, let's say, cloud simulation packages, where you see that, of course, for UberCloud, it's very important to team up with those. So for people like ANSYS, which does lots of aircraft design and CFD packages, it's very important to team up with those to have a solution already in the containers ready for ANSYS. But of course, that's where you just start. Maybe there are many different other packages. Some of you are maybe familiar with MATLAB, that's still used in production outside in industry. You have different other packages like OpenFOAM, I showed it earlier, and many other smaller ones that you maybe also do for very specific purposes. So hence a very rich field, but by sticking to this de facto standard you learned today on Kubernetes and Docker, and then here is an example of OpenFOAM, where you, for instance, can have in an industry setup here, when you want to create a new company or factory somewhere in an area, which is for industry, and you have to basically show the government or show the, let's say, certain, let's say, legal constraints, how your, let's say, your kind of chimney will distribute essentially your elements of the production into the, let's say, environment. You have to basically show that perhaps and simulate this a little bit, so that not, let's say, if you create this company or factory somewhere, you suddenly have a living quarter neighborhood seriously affected with this. These are things where you use OpenFOAM, for instance. So also, of course, again, this is something we tackle more in the HPC course, because it requires then also enormous computing. But you see with UberCloud, you can do this nicely also in cloud computing environments. Just as another example, ANSYS was one more commercial example, very costly in a way, but they also support open source packages like OpenFOAM, which has a huge community behind it to solve CFD problems. And this is, of course, another, let's say, side effect of getting more known, of getting more adopted. Some of the application use cases, this is something where we can spend, of course, lots of time, and I don't have the time here in the lecture series to go in all the different areas you see, from essentially this car crashes to biomedical engineering, to essentially deep learning, so AI elements, combining them maybe with the fluid flow, a very interesting field these days that we also tackle in the Center of Excellence RACE. If you remember one of the seminars you attended here, basically where I invited you to, this is a basically new field of research combining these engineering elements with AI, which gives you hopefully lots of insights in the future. You have traditional elements like CFD simulations of wind farms, of wind turbines, which is extremely computational demanding. Alone, the, let's say, effects of one wind wheel is computation expensive. And if you wouldn't have whole wind farms as it is today, and to simulate the output is really extremely computational demanding and almost not really fully understood right now. But here the power of computing and clouds is, of course, another helper. And you can go on and go on. Airflow, you see here basically this Advania HPC flow cloud that I was actually alluding to, which is here from Norse and so on, provided also this very much involvement of Icelandic players. In one of the last Icelandic HPC workshops, actually, they have been presenting the solution. You have been here in the course in the second. In the first, basically, we will make the slates available. There was also at Norse discussing about HPC flow. So in other words, things are happening in Iceland, right? So that's my key message also here, orthogonal to this. And we will also have lots of contacts in this. If you have interest to work in this field, there are lots of companies that require experts in these areas. Now, as I said, wind turbines, aerodynamics, creating aircrafts, this is all a big enterprise. And just to give you some numbers, when you think about manufacturing, which is here savings per HPC, what is the profit by doing this, right? Why should people, proper engineers, going to HPC? And here the example of manufacturing is really 83 million increase in revenue as an example, or basically just 20 million increase in profits or cost savings if you do the HPC wave in costs of doing it the manual way. And this is just one independent research here in one specific area. And of course, think about this goes to life sciences, defense, retail, oil and gas, all of these areas which are traditionally, let's say, extremely important in terms of return of investment for companies. Now, when you think about the tool sets and what are maybe the disadvantages a little bit and cloud container benefits, you would say, you have the left-hand side, which may seem like it is negative, and you can turn it in a, let's say, more positive idea if you use the cloud computing. These are not totally, let's say, obvious directly, but of course, if you use the simulation techniques and the clouds and HPC, chances are that you really, when you do the whole product life cycle from the concept up to the maintenance at the end, you really basically have lots of room for cost reduction. Especially, usually you would have an extremely cost of change and lots of different IT tools you have to deal with. So by doing this containers with this UberCloud, you in a sense countermeasure all these problems. You're relatively agile. You can, as we said earlier, also combine new elements, like for instance, databases with this red Iris cluster or certain workflows on Kafka. And then you have the whole idea of all these different prepackaged parts like ANSYS, we said already, or MATLAB maybe. So in a way, a stack which is very flexible to work with. You have here an example in MS Azure, but as we said earlier, we can really move away very quickly. And with this, you're not really bound when you do your concept to one different cloud computing environment to do it then maybe later in someone else's environment. So in a way, what you summarize would we basically have this engineering life cycle of innovation, design, then create the product, operate it, and being then really as product means maintenance and so forth. And it's a continuous cycle. You want to improve the product. You need a certain platform to build all of this. And there the containerized environment is just beautiful to support this. So in a way, you turn this HPC, which is perhaps more the academic area of dealing with these problems, more into a cloud setup in a very admittedly niche market. But of course, we have seen also this niche market is very rich in terms of return of investment when you talk about oil and gas, car, or aircraft engineering. And I encourage you to maybe go to the website to explore more. I think I have shed light a lot of this now, basically how that works. You can imagine directly that we have this Kubernetes environment, which means a very flexible way of deploying all of these different UberCloud containers, perhaps on different, let's say, infrastructure, which also the video was showing you. Right here, you're much more, let's say, technology diverse. Some elements maybe run better on CPUs. We have learned deep learning probably should leverage GPUs by now. Apache Spark should be very powerful in terms of RAM. And you go on and go on. You can actually combine this based on the infrastructure and hardware that you have and be a very flexible software in order to have your containerized setup. And with this, of course, you're very flexible to engage in these, let's say, large scale problems you may have, but you're not really bound to the underlying infrastructure, right? You can still merge from MS Azure relatively easy to AWS for certain services. Maybe then you go to interesting accelerators on another cloud provider. So you're kind of very flexible by having these systems in between. At the end, just for some related work and some pointers here, Singularity is an environment that we also support, for instance, in our Jülich Supercomputing Center, and many academic systems actually work on Singularity. But if you look into the details here, it has recipes similar like essentially our Docker images. So in the end, there's a high interoperability to Docker in a way, how you do this. And we also doing this in practice, so we can say it works to 90%. Here and there, you have to recraft some elements in it, but chances are that maybe some installations just support Singularity. And then when you think about the scheduling really approach, we don't talk much about here, would be maybe another lecture. We talked about orchestration, but another aspect to it is also then essentially the scheduling on all of this on different hardware and so on, and executing perhaps different frameworks. We see here an example with Hadoop, which we learned in one part of the course, but then the MPI schedule maybe takes more part of the CFD simulations we have seen in the engineering domain. For this, you need really tools like Apache Mesos or Zookeeper to really have the bigger picture. And all of this would be just other lectures, but we kind of lack the time in the cloud computing course to cover all of the open source packages here. That's why I refer to you to more the references and essentially just summarize now what we see here with UberCloud, maybe in another video. Again, a little bit longer, but I think it shares you an interesting approach and a very unique niche market, basically, inside the UberCloud.
In this video, you'll learn how to run Ansys Icepack on cloud-based workstations and clusters. First, let's look at how to run Ansys Icepack in parallel on a workstation, utilizing all of the cores that we have available. First, open Icepack. You can now choose if you want to start a new project or open an existing one. We're going to open an existing one for this case. In my case, the project is located on the desktop. After the model is opened, go to Solver, Settings, and then Parallel. In the Configuration pane, choose Parallel, and in the Parallel Options pane, set the number of processes. In our case, we have 8 cores, so we set the number of processes to 8. Press Accept. Now you can go to Solver and choose Run Simulation. In the dialog window, click the Start button, and your computation will start. Now it's time to look at how we can run IcePack in parallel on a cluster. So the first step is to prepare the host file that tells ANSYS on what computers to run their simulation. To do this, go to HPC user's home, create a new text file and name it hosts.txt. Open the file and also open the file mpd.hosts. mpd.hosts contain the compute nodes in the cluster. We need this information for our hosts.txt file. We want to add one line for each core that we want to use. And each of our compute nodes has 8 cores, so we need to add in total 16 lines. For the first 8 lines, copy the name of the first node for mpd.hosts. Go to hosts.txt and paste this text 8 times. Repeat the procedure for the second node. We're now ready to start the job. First, let's open IcePack. When IcePack is open, either open an existing project or create a new one. We will open the same project as in the first part of this tutorial. After the model is opened, go to Solver, Settings, and then Parallel. In the Configuration pane, choose Network Parallel, and in the Network Parallel Options pane, you must now find the hosts.txt file that we created. If it isn't already selected, click Browse and find the file, and then click Open. To make sure that you have the right file, you can click Edit. This will show you the contents of the file. Now you can click Accept. To start the simulation, go to Solver, click Run Simulation, and then press the button Start Solution. Your model will now compute.
So this was a more practical exercise, show you, of course, still some practical insights in all of this, because in a way, it would be good to have a more practical lecture on this, because it's also very much conceptual aspect of how to use clouds. We would perhaps do Docker and Singularity interoperability in our demonstration. But the point is that in this cloud course, we cannot have all the different things really shown, because it's a very large topic. You have seen from really hands-on machine learning, hands-on data mining, on big data mining, really. And now we basically had finally also then something about these Docker images and so on. It would be just too much for one course. So I think in the future, we definitively probably see something like Docker courses, or at least the open source packages in a broader sense. So things like Apache, Mesos, Kubernetes clusters, and so forth would be, of course, a complete other section of distributed systems to teach. And this is something, of course, which is very relevant. But of course, in this, let's say, one lecture today, you had a good insight of what is really relevant also to know when you go to a job interview and people will say, well, you're data scientists. So what about essentially all the, let's say, software packages around it? And you know already the Apache Hadoop, you know, Apache Spark, which is one ecosystem. Another ecosystem is really the deployment and management of containers with Docker, with Singularity, with Mesos, with Kubernetes. But that's all really for the lecture today. It was a very, let's say, different facet on cloud computing. Hopefully you understand that. And actually in the next lecture, which follows on Thursday, we will have yet another vision change, essentially, or view change, if you want, on cloud computing when we talk about OpenStack, which means essentially how you create your own cloud in your own organization. Until then, see you on Thursday.